Now that we have a basic notion of paging, let's look at virtual memory. So remember, when you're running a program, typically you're not using most of the instructions in the program. Take, for example, PowerPoint or Word applications. There are many options in such Office applications that you're not even aware of. And even for those that you're aware of, at one instance of running those applications, like at the moment I'm running PowerPoint. So at the moment, I'm actually not using many of the instructions of PowerPoint. On some other day, I might be using them, but not at the moment. So why do I load all those instructions into the memory? Actually, that's if you try to load the whole program, all instructions of the program into the memory, you will realize that it's really huge. There's almost no memory left in your system. So it is better not to bring the parts that are not needed, because some of those instructions, some of those routines are for exceptional cases like error handling, some unusual routines. There are sometimes very large data structures. There are, many instructions, many routines that are meant for some specific kind of users, but not for the others. So why bring them all into the memory? In virtual memory, the basic idea is to partially load the programs into the memory. Only load the parts that are in use and not the others. Also, keep in mind that even for the same user, some parts of the code are executed only once. For example, for initializations, you do the initialization only once. Once you've done the initialization, until that process is terminated, you will not run the initialization functions again. So the parts that you are not using at all, or the parts that you have used once but then not using, so in other words, the parts that are not frequently used, you don't try to keep them in memory, and therefore you will have more space for more processes and you will have better CPU utilization. So the virtual memory concept introduced by Özal Babaoğlu is the separation of the user's logical memory space from the physical memory space provided in the system. It's taking only the parts of the program that are needed, and therefore virtual memory allows the sum of the logical address spaces of all processes combined. If you take that sum, it is far larger than the physical memory available in the system. In fact, virtual memory even allows us to have processes, a single process even larger than the physical memory, as long as not all of that address space is in memory at the same time. It also allows the address space to be shared between several processes. Remember, this comes with paging itself. Allows for more efficient process creation. You can create the processes faster, as we will see. And since processes have less space in memory, you can have more programs running concurrently, and less I/O is needed to load or swap the processes. So the virtual address space is the logical view of the process, logical view of how the process is stored in memory. The virtual address space typically starts with address 0, and since it's a virtual address space, it appears to be contiguous. However, in reality, in the physical memory, it's not contiguous. Furthermore, not even all of the virtual address space is in memory. and we will make of the swap space to swap out some of the pages, not the whole process maybe, but swap out some of the pages. Virtual memory can be implemented by demand paging and demand segmentation, in which we even skipped segmentation itself. So we will not look at demand segmentation either because it's not being used anymore. So we will be basically talking about demand paging. So if you take any process has, first of all, the text segment, which contains the code, the binary instructions for that program, for the corresponding program from which the process was created. You have your data segment for the global variables, which is typically initialized. That's why in C, the global variables are initialized to 0, but not the local variables, because the local variables are on the stack. The stack contains the entries for the functions during the lifetime of the process. Initially, the stack is completely empty, but as soon as the process starts execution, you call the main function. Therefore, an entry will be created for the main function. As main is executing, it might call other functions. So every time a function is called, an entry will be created on the stack. So the stack keeps growing as functions are called. But when the functions complete, the stack also shrinks. So during the lifetime of the process, the stack grows and shrinks. Finally, in normal termination, you will reach the end of main function. Now, when you're in main function, that means all other functions are completed. So main would be the only entry in the stack. And when you reach the end of the main function, the stack will be completely empty. And that's also the end of the process. So the address space will be completely released. During the execution of the program, if the process is making use of dynamic memory allocation, that means using malloc or new or similar statements, functions, to dynamically allocate space, then that space will be taken from heap. So again, initially, when the program starts, the heap is empty. When you say new or malloc or calloc, you get some space from the heap. You call new, once again, some more space, some more space. When you free those spaces, then they will be released. So the heap also grows and shrinks. The only difference being that the stack is a stack, as you know from data structures. So the stack grows and shrinks from the top. The top goes up and down. By the way, in this figure, the smallest address is drawn at the is given at the top, at the bottom. Sorry. So 0 is here, max is here. If you just invert the figure, it will look actually much better. The stack grows and shrinks, but you don't have any gaps in the stack. So in other words, if function f calls g, g will be on top of f. F cannot complete before g completes. So first g has to complete, then f. That's the idea of a stack. That's not the case with heap. You allocate space for A, then for B, then for C. You might release the space for A, so there will be a hole there. Again, that's something we cannot deal with that. But the important thing here is some fixed amount of memory is reserved for code because the code is not growing. Some fixed amount of space is reserved for the global variables, for the data segment. And the rest is left for heap and stack. Heap or the stack is not given a definite size. The rest of the process address space, virtual address space for that process, is given to heap and stack. These grow and shrink during the execution time of the process, as long as the sum of heap and stack together does not exceed that given space, which is here, all the space, you will not have any problems. If the sum of heap and stack goes beyond that, then you will have a stack overflow or heap overflow. So when programs are running, each process has its own code, data, heap, and stack. However, you will also have some shared libraries from dynamically linked libraries, but the same library, shared library function will be also used by another process. Okay, so that will be that piece of code will also be used for another one, for another process, another process, another process. So what you do is you put such shared library instructions in some shared pages and add these shared pages into the paging tables of all such processes. So you still have a single copy, but from the point of view of individual process, this process thinks these shared pages are here, and this process thinks they are here. Actually, physically, they're outside both of the processes address, real physical address spaces, but in their logical address spaces, virtual address spaces. Now, coming to demand paging. Demand paging is paging as we have discussed in the previous video, but the idea is when the program starts, you don't bring all of those pages into memory. You keep them typically on the swap. You don't want to put them in memory. So this way, you can have a small portion of the process in memory. So you just bring the parts that are needed. This provides us to have less I/O and avoid unnecessary I/O operations. The processes require less memory, therefore starting the processes, loading them or completing them provides faster response, and you can have more users or more applications running in the system. It is similar to paging we discussed earlier, together combined with swapping. When a page is needed, the CPU generates an address, and you try to reference that address. Now, there are two possibilities. Either it's an invalid reference, like you had a pointer error, the pointer value was wrong. In that case, you should be terminating the process because the process tried to execute an invalid operation. It's trying to access an address that doesn't belong to it. Okay, so in that case, it should be aborted. However, it is possible that from the programming point of view, there was no error, but the operating system, just to save from memory, preferred not to put that page in the memory. In that case, it is not the fault of the process, it's just a preference of the operating system. So the operating system, in this case, does not punish the process, but the process cannot proceed either because the item it wants is not in memory. So it pauses the process for the moment. Pay attention, we're not terminating it. It's just paused at the moment. You bring the required page from the swap into the memory, and once it's available in the memory, then the process is resumed, so it can continue from where it was left. So there will be some delay because the requested page was not in memory at that point, but now it's in memory. It can resume. There will be some delay, but it will work. In demand paging, we typically use what's called the lazy swapper. So the lazy swapper does not swap a page into the memory if nobody is requesting it. So in other words, it's delaying the swap in operation for that specific page. we typically call it also page in. So it delays the page in operation until that page is specifically requested. The swapper that deals with pages is called, by the way, the pager. So with swapping, the pager guesses which pages will be used before they're required. So it brings those pages into the memory. It also works the other way around. It estimates which pages will not be required and swaps them out also. So the pager actually is a utility that is proactive. That means tries to estimate the need for the pages before they occur and does the proper swap in and out operations. Now, this guess, of course, is difficult. And since this is a guess, it might fail at some point. Okay, so if that happens, we will have this point here. That process will be temporarily suspended. We have to page in the page it requires using the pager. And when the page has been brought into the memory, that process can be can continue, it can resume. But we would like to minimize this happening as much as possible. If you can make good guesses for the use of the pages, then you have a good pager. How do you determine the set of pages that are being frequently used, that are going to be used actually? We don't care so much about the past. The past has happened, whatever it was. But we would like to guess the near future as good as we can. So we need some new memory management unit functionality which will implement demand paging. So if the pages that are needed are already in the memory, they are memory resident, then there is no difference from non-demand paging. It's just the regular one. But if the page you need is not in the memory, then you need to detect and load the page. You need to first detect that this is not a memory access error, but this is just because of the operating system. Find the corresponding page, bring it into the memory, and then resume the process. This should be done without changing the program behavior. In other words, the program should not be aware of this. Only thing is the program is slightly delayed. And also the programmer should not do any changes in the code. So this should be done completely independent of the process. So this thing that valid invalid bit concept once again. What happens when in the page table some pages are not in memory? So with each page table entry, so remember here we had a valid invalid bit. Okay, so it is valid for memory resident pages and invalid otherwise. Initially, valid invalid bit is set to invalid for all entries because you don't want to bring in any entry. The first time you try to access an address, it will cause a page, what we call a page fault. Page fault is not a real error. Page fault is trying to access a page which should have been there, but it's not there. So during the memory management unit address translation, if the valid invalid bit in the page is invalid, this is a page fault. And as we discussed earlier, the corresponding page will be brought in. For example, here, in this example, from the point of view of the programmer and from the point of view of the process has contiguous memory going from A all the way to H through pages from 0 to 7. In reality, only pages 0, 2, and 5 are in memory. They correspond to A, C, and F in these frames. Only for those frames, we have valid entries. So the valid bit is set accordingly. And for the rest, it's invalid. In the swap, you actually have the copies of these. Okay. So when the process, for example, tries to access, let's say, page 4, when it tries to access E is in page 4, it goes to the page table. In row 4, it sees that it's invalid. So this is a page fault. The process cannot continue. The process has to wait for the pager to find, first of all, an available frame. Once an available frame is found, it will find also the corresponding page E in the swap, bring that into, let's say, 12, frame 12, and then write in this field here 12 in row 4 and convert its valid invalid bit into valid. And then resume the restart, not the whole process, but whatever instruction caused this page fault, that instruction should be started again. So this is actually explaining what I already told you. And this is a graphical notation of the steps while handling a page fault operation. So there was, for example, an instruction like load M, which had a reference to this specific page table entry, which was invalid. So this caused a trap to the operating system. The process was working, but the process caused a trap. So the process is suspended. Now the operating system is working. The operating system realizes what the problem is. It goes to the backing store, to the swap storage, finds the correct frame there, finds a free frame in the physical memory, brings this missing page into this free frame. This frame is not free anymore, so it should also be removed from the list of free frames. Then the frame ID of this frame should be written in the page table, and this invalid bit is now converted to valid, and then this instruction load M starts once again. So in the extreme case, a process starts with no pages in memory. The operating system will try to execute the first instruction by looking at the program counter and find that it's not in memory, so it will cause a page fault. So the process, the moment it's getting started, it's just suspended, and it will find the page, bring it into memory, and resume that instruction. And for every new page access, now hopefully the following instructions, many of them will be using that page that has just been brought in. But at some point, you will need to access an address in another page, then another page fault. So this is called pure demand paging. However, a given instruction could be accessing multiple pages. So it could cause multiple page faults, like add A and B, put it in C. A, B, and C could be in different pages because they're in different places in the memory. So the pain could be decreased by the locality of reference, or another name for this is the principle of locality, which means not guaranteed, but typically in most cases, if you access this memory address, the next access will be somewhere in the neighborhood. That's what the locality of reference is. Wherever you're referring, the following references most likely will be in the similar area. If not, I'm sorry, that page fault, additional page fault will occur. But once you have the page fault, hopefully the following ones will be in the neighborhood. The idea is once in a while, page faults might occur, but we want the page faults to be very rare, which implies consecutive instructions typically work with variables in the same locality. You need some hardware support for demand paging. You need page tables with valid invalid bits. You need some secondary storage for the swap space. You need a way to cause a trap because of page faults and then restart the instructions. So in summary, these are the stages in demand paging. You first cause a trap to the operating system, then this requires a switch from the user mode to the kernel mode. So you save the user processes, registers, and process state. You determine the interrupt was a page fault. Then you go to that page fault handler routine. Check that the page reference was legal. It's not an illegal memory access, but it's just a simple page fault. And determine where the page is on the swap space. Issue a read operation from the swap space into a free frame, which implies first find a free frame. This is I/O operation, so you have to wait in the queue for this swap device until that transfer of the page from the swap into the memory is completed. You have to wait for the device seek and or latency times because of the disk access and also for the transfer. While waiting for that process to do the page in operation, you should schedule the CPU to some other process. And while other processes are running, ultimately this page in operation will complete. So you will receive an interrupt from the disk I/O subsystem for I/O completion. And now you should handle this operation. So you save the registers and process for that process that is running. You determine that this was an interrupt from the disk, from the swap device. You correct the page table with the frame number where you're writing this page that's being paged in, and also updating the valid invalid bit and other tables to show the page is now in memory. And you should wait for the CPU to be allocated to this process again. So actually you should wait for the scheduler. And when it is done, you will restore the user's processes, registers, process state, the page table, because you have done a context switch from one process to the other, and finally resume the instruction which was interrupted. There are three major activities here: servicing the interrupt, reading the page, and restarting the process. If you write this interrupt service routine carefully, it takes just several hundreds of instructions. Page reading takes a lot of time. You'd better have a fast disk there used for swap. And you need to restart the process so it's simple. So what is the probability of having a page fault? Let's assume the page fault rate is P. Since it's a probability, it's between 0 and 1. If it's 0, that means you have no page faults. There's no such system. If it's 1, that means every instruction causes a page fault. This is terrible. This is typically not likely to happen. So the effective access time, again, is the weighted average. With probability P, you have a page fault, remember. So in the case of a page fault, you have to handle the page fault, so it has an overhead. You have to page out a victim to open up space for that page to be paged in. So you have the cost of page in, but to be able to bring it into the memory, you should find a victim page and take it into swap to open up space for that. So it is one page out, one page in, and page fault overhead in general. This weighed with the probability of having a page fault. If there's no page fault, then a simple memory access. So assuming that the memory access time is, let's say, 200 nanoseconds, and average page fault service time is 8 milliseconds, then the expected, effective access time would be 200 plus p times almost 8 million for 8 milliseconds. So if you have a page fault of 1 over 1000, so out of 1000 memory accesses, only one of them causes a page fault. 999 are just finding whatever they need already in memory. Then the effective access time would be 8.2 microseconds, which is 40 times slower than this 200 nanoseconds. So it is actually terrible. It's quite slow. So if you want to limit this performance degradation due to demand paging, remember, demand paging helps us in many aspects, but it definitely causes a slowdown. If you would like to limit that performance degradation due to demand paging below 10%, the page fault rate should be less than this value, which corresponds to a page fault in less than one page fault in every 400,000 memory accesses, which is quite really slow. Quite low. So one solution to speed up the system is copy on write. In the copy on write, for example, when you have two processes, parent and child processes, the parent and the child process initially share the same pages in memory. That means when you create a child process, we always said you copy the whole address space. In reality, you don't copy much. Of course, you have to create a new PCB. It is a new process ID. So some things have to be created. But for the pages of the child process, you just share it with the parent rather than copying them all together. If either process modifies one of those shared pages, and now you have a problem, like the parent and the child. Now, first of all, remember the instructions are the same. Okay, so the text segment need not be copied. It could be easily shared. But also, that's also true for the other pages. Initially, they're all the same. Remember, the child process even has the variables with the same values. The only difference, remember, was the return value. However, as the parent and the child continue their own path, they will be changing their variable values. Also, they will be calling their functions. Therefore, the stack will also change. As this is happening, only that page that has been modified, either by the parent or the child, doesn't matter. But it means now those pages should be different. Only in that case, you create a copy and modify your own copy. For all others, the pages are the same. Now, what if the child process, after fork, immediately calls exec? Remember, fork and exec need not always be used together. But in many cases, yes, fork in many cases is followed by an exec. Now you say fork, you copy everything, and then you say exec, you overwrite the whole thing. So why did you copy all of it? So there is a function named vfork. We talked about this earlier in some earlier chapters. There is another variation of fork, which is called vfork, which will just make use of copy on write. And when you say exec, since it has not copied anything, it will be quite efficient. So this is how things work in the case of parent-child, or in general, when you have a shared page or shared pages. In this example, we have two processes, process 1 and 2. They're sharing 3 pages, A, B, and C. So actually, there is a single copy of A, B, and C, and their page tables are pointing to the same pages. When one of them, like process 1, modifies something, not the whole page, even modifying 1 byte is enough. When it modifies 1 byte of page C, you need to have the full copy of that page. You cannot just say, I'm just creating a copy of that byte. You have to copy the full page because it works in terms of pages. So process P1 gets its own copy of page C and makes the modification there. So process P2 will not be aware of that. Of course, if it's not shared memory. If it's the case of shared memory, then of course you don't make a copy. It's the same copy.